So today's lecture is face recognition, and this lecture, well, there's going to be a series of lectures on face recognition because it's a huge topic. And as I said last time, high-level vision used to be based on model-based methods. That's what we have described thus far for high-level vision, and that was very typical of the 1970s, 1980s, and 1990s. And then around, and that includes, by the way, face recognition. So there was a professor here at Ohio State that was one of the very first people to do face recognition, meaning recognition of identity, and I think he did gender as well, from profile views. And at that time, all they could do with the camera is just to extract the contour of the face, right, and try to match that shape, right, with shape analysis methods. And then another professor at CMU also did a very famous thesis on that, also based on model-based. And then in the 1990s, and then especially in the 2000s, people started developing new tools for face recognition that became very popular, very powerful. These are most of the tools that are still in use today in face recognition technology. And that's what then was extended to or used to build good object recognition systems. And later that was extended with, so most of the methods that we're gonna describe today are based on least squares, linear least squares mostly, and extension of linear least squares. And then later was extended to nonlinear least squares, mostly with deep learning, as we have seen. Okay, we've created the SEND methods. All right, so remember in model-based vision, right? In model-based vision, the key concept is that we ought to learn a model, right? And by that model, we mean a geometrical model of the object, right? And mostly by this we mean shape, either 2D, 3D, or 4D shape. Now, an alternative that was considered by people mostly working in face recognition is that if I have an image of a face, and for now I'm just going to assume, and we'll talk about this in a second, I'm going to assume that I already have the face centered in some image. And then if I have an image of a face, then I can divide, let's say this image rather is given by a number of pixels, right? So an image is nothing else than a matrix with its corresponding pixels. And then what I can do, as we have done at other times in 5460 and here, is that I can take the value of the first pixel and write it as the first entry of a vector, and then take the second pixel and write it as the second entry of a vector, right? And the third as the third, and so on until I get to the last pixel in the first row, and then I start with the first pixel on the second row, and so on and so forth, until I get to the last pixel here, the last row, last column, right? And that will be XP. And that gives me a so-called vectorized image. So you'll see this called many times as a vectorized version of the image, right? Now, we also assume that this vector then is represented in a space of p dimensions. Typically, we're going to assume that this space of p dimensions is it's in the real domain. It's defined the real domain. Now, this is a little odd because pixels are not real numbers, right? If you have 8 bits per channel, then you have values from 0 to 255, but these are integers or natural numbers, right? They're not real numbers. But we're going to write them as real numbers because we want to treat them as random vectors, right? And we want to apply statistics to them. And it's just convenient to do so. All right. So if this is my image I, then what I'm going to do, I'm going to write that this vector xi it enters xi1, xi2, xi3, up to xip, right? And that is going to give me a vector in some feature space, right? My space Rp, in that case, if it were 3 dimensions, which is all I can write, this vector would be something like this, right? This vector xi here. Now, for clarity, what I'm going to do, I'm just going to indicate that vector by a point, right? And that's where the vector ends, right? And that vector gives me the coordinates, right, of the xi1, xi2, xi3, and so on coordinates, that these coefficients that I have here in that space of the real space of p dimensions, right? So this is one image. So there might be maybe the first image. They might take another image of another face. It'll be here. Another image of another face maybe here. Another one, and so on. And each image can now be represented as a vector, which I'm just representing here as dots, right, of the multiple images that one can have of faces, right? Now, remember that Rp is the space of all possible images, right? All the possible images you can ever take, right? Because any image can be vectorized. An image of p dimensions, or p pixels, can be vectorized in a p-dimensional vector. And therefore, every image will be a vector in that space. Now, because the images that correspond to faces are very similar to one another, and there's a technical term to say that to describe this, which is they are highly correlated, right? Because they are correlated, they are going to span a subspace of that Rp space as we have seen before, right? And we know of a technique to find these correlations, and that technique is anyone? Least squares, very good. Which for this, what's it called? To find these correlations, what's that? PCA, very good, right? So you apply PCA, principal components analysis, and that will give you the basis vectors. The eigenvectors is going to be the basis vectors that span that subspace, right? The eigenvectors that are associated to 0 eigenvalue or very, very, very tiny eigenvalues can be discarded because they span part of the space that do not describe a face, right? So if I have, remember my training set, that is my xi's, I1 through n, right? And I have all of this here from 1 through n. Then I can compute my mean and my covariance matrix, right? So to do that, we compute the what's called, I shouldn't say the mean, I should say the sample mean, right? Let's call it mu, which is n inverse, the sum over all I of all my xi's, right? I mean, obviously. And similarly, I can compute my simple covariance matrix, right? Sigma x, which remember is the sum over all i's of xi minus mu times xi minus mu transpose, right? Right? And with that, then I can compute my PCs are given as an eigenvalue decomposition of the covariance matrix V lambda, where V is a matrix whose columns, right? the columns of this matrix are the eigenvectors, and delta is a diagonal matrix of corresponding eigenvalues, right? And remember that generally we assume that the eigenvalues are sorted from largest to smallest, and the smallest one is larger or equal than 0, right? And then in general, what we could write is that for some value, say q, right, this is going to be larger or equal than lambda q plus 1, which is equal to all the ones up to p. This is either p or n, depending on how you compute the sigma x. And this is 0, right? Or let me say, instead of equal, why don't we write approximately, right? Because it may be very tiny, but they're approximately 0, right? And then what we want is to define that the space here with the basis vectors, the vi's, right? So it's going to be here v1, v2, and so on. Actually, it's going to be v1 rather and v2, right? v1, v2, and v3, v4 up to vk, right? And that defines a hyper, or the subspace of that of faces. Okay, so if you want to define these these PCs for the faces, these are called the this method is called the Eigenfaces. And here, what you do, you define the subspace with the first R eigenvectors with R a smaller or equal than Q, right? Okay. And by the first ones, I mean V1, V2 up to VR, right? Which are the ones associated to the largest eigenvalues. Now, this method is actually due to a good friend of mine, Matthew Chirk. And Matthew is going to give a talk here. I've invited him to give a talk here in our department. I think it's the 18th or the 19th. I don't remember exactly, but I'll check. I think it's I'll let you know. I'll post it in Canvas, but I think it's the 18th or the 19th. So I really encourage you to go to his talk. I promise a very interesting, good talk. All right. By the way, Matthew Chirk now is the president of the Toyota Technical Institute in Chicago, which is a university in downtown Chicago in Illinois. So, good talk to go to. And he'll be talking about the ethics that I mentioned that we probably won't have time to cover. All right, so now faces are going to be defined in this space, right? Or rather, even better said, this space defines faces, and therefore you can call this space the eigenfaces. Well, the eigenfaces are the basis vectors, but the eigenface space, you can just call it the face space in general, right? Any space that you define that defines only faces would be called the face space. And you can see how you could do that not only for faces, but for any object that for whom, or for which rather, the images of that object are highly correlated with one another, right? The images do have to be correlated because they have to define a subspace. If there are no correlations, then that's not going to happen. Linear correlations, I mean, obviously. All right, so now, first thing that we want to do is face detection. Right? So the first thing I want to do is to design an algorithm that, given an image, it tells me whether there is a face in that image, and if there is, where is it? Okay? And here I have been given this already detected or well-centered images of faces as my training set that is given to me, right? That someone has created this data set. Remember, someone has created a data set to make sure that this is well done. During this data set creation, someone has taken care that the size of the image is constant across all the faces, that the eyes are approximately located in the same location of the face, that the mouth is located in the same, of the image, that the mouth is located in the same position of the image, and so on, because otherwise I would just be comparing apples with oranges and there would be no correlations, and therefore the PCs would make no sense, right? So we'll talk more about this later, but someone has done this for us to give us some training, some good training data. But now we have a new image here, right? And there is a face, say here somewhere, right? And in that image, and I don't know what it is, okay? So what I'm going to do, I'm going to center a window at every pixel in my image, right? And say a window of p pixels, like that one there. And then I'm going to slide this window first across the first row, then the second row, then the third row, right? And what I'm going to do, each of these windows, because it's a p pixel window, it's going to give me a new vector. Let's call this vector, just x, okay, without the I, right? So I have this vector x, and of course this vector x is also defined, actually. Let me do this here because some of you may not see there. So this vector, remember this is RP, right? And we have here in RP our subspace that defines faces. So our face space, it's here somewhere, right? So let's call this subspace S that defines my faces. And now what we have here is I have my vector x, which maybe it's here, right? And then what I want to do is I want to compute the distance of that x to that subspace, right? And I want to compute, for example, the orthogonal distance, right? The orthographic projection of that point on top of that plane. Right? So if I had taken here to define this PCA space, this S space defined by the matrix M, which contains the first, we said, R basis vectors, the R eigenvectors that I have extracted, then I can project my vectors, right, onto that space, right, my xi's, by simply mapping xi transpose M, right? Correct? Yeah? See that? Okay. So I can do xi transpose M. Let's call this maybe xi hat. How about that? Now, note that I can also go back, right? I can reconstruct my image. I can do xi, say tilde now. It's equal to m xi hat, right? So here what I'm doing is I'm projecting my training images onto that space that defines faces, right? And then here I'm projecting it back into RP, right? Yes? And I can do that because if that subspace truly represents faces, the amount of information that I have lost on an image of a face is pretty much nil, right? It's very small. You see that? So the reconstruction of my face has to be almost identical to the original face. I'm going to lose something, obviously, because I have lost information, but it should be very minimum, right? Okay. So what that tells me is that I can compute the distance, right? Let's call it the distance, what did I say here, dh, Okay, I don't know. Let's say h. I don't know why I selected h, but anyways, of my xi minus the xi reconstructed. And let's say I just use the classical reconstruction error function of least squares, right? So the 2 norm, the square loss, the 2 norm, to determine that distance, right? Now, if I learn this, right, I can learn, or I can define what's the difference between the original image and the reconstructed image for my training set, right? And now what I want to know is if I apply this metric here, dh with x, so I get x minus x tilde, its reconstruction, right? Is that something that is similar, right? That distance is within the range of the distances of my training data, right? So, for example, there are multiple ways to do that, right? You could take the maximum of the h of all your training samples, right? Let's write it like this. The maximum distance, right? And if this is smaller, now that the maximum distance, if this dh, excuse me, let's call it dh prime here. For testing, if this is smaller than that maximum distance of the training samples, then I say that this window has a phase, right? So I have detected, phase detected. And if not, that window does not represent a phase. But you could also say it's within, you compute the mean distance of this dh for all your training set, and then compute 2 times the standard deviation. And then you want to make sure that you're within this 2 times the standard deviation from that mean, right? So it's smaller than 2 times the standard deviation, because there could be a lot of outliers here, right? So the maximum may not be the best way to go. That's just a very simple way, right? That one of the first ways Matthew actually came out with this idea to just compute the distance to that subspace, right? And that tells you if the distance to that subspace is smaller than that threshold that we have determined, then that window represents a phase. And what's going to happen? What's going to happen is, let's see if someone can answer this. If I take this image right here that does not contain a phase and apply this equation, when I reconstruct the image, this window here, what am I going to see? What's that image going to look like? All right, first of all, is it going to look like the original image? No, good. Why not? So when I project my xi, or my window x, onto that subspace, what am I really doing? I'm finding what? What's that? On that subspace, and what do these coefficients represent? No. No. What does a point, a vector on that subspace represent? A phase. If I now take that point that I have selected on that subspace, a vector, and I reconstruct it as an image, what will I get? A phase, right? That xi hat is always going to be a phase by definition, because that subspace only represents phases. So I'm finding the vector that's closest to my actual window vector, right? Find the vector that's closest to it, but that vector is by definition a phase. Therefore, when I reconstruct, I'm going to get a phase. So my xi hats are always going to be phases. And when I do a simple Euclidean distance or any other type of distance that you want to use, right? You can use any p norm or any other more sophisticated distance. once I do that distance measurement, I'm comparing a face with something that's not a face. It's going to be a large number, right? So I'm only going to detect faces when both vectors are faces, and that number is very small, right? Is that clear? Yeah? All right, awesome. Now, this obviously can be quickly or easily extended by, for example, assuming that the data is distributed according to a normal distribution. So let's say that my data is known to be distributed as a normal distribution. Then what I can do in my space here, right, I can first compute the subspace S, and now here I can compute the distribution, the normal distribution of all my vectors, right? So my vectors of my training set are going to be hopefully normally distributed in here. And now I can compute that, I can estimate that normal distribution, right? And then my distance, I can call it the Mohanowitz distance, mh. Here is going to be given by xi hat minus mu hat, where mu hat is this reconstruction, right, given, or this projection rather, given here as the mean of the Gaussian that I'm estimating, times sigma x hat inverse times xi hat minus mu hat transpose, right? Oops, I'm sorry. This is not the covariance. This is a metric. Okay. So xi hat minus mu hat transpose times the covariance matrix that defines, so this is this covariance matrix, right? This covariance matrix is this one here, right? Sigma x hat, which is the same as m transpose sigma x m, right? Which is a projection of sigma x onto that subspace S, right? Make sense? Yeah? And the same obviously applies to mu, right? So this mu, this mean here, this mu hat is equal to m mu, right? No, actually, I'm sorry. It's mu transpose m, the other way around. Mu transpose m. That makes more sense. Okay? And now, instead of using dh, right, we rather use this metric here, because obviously that defines faces even better, right? Because faces are not every single point on that subspace. They're probably just located according to some distribution on that subspace, right? Now, if you take my machine learning course, you will learn about other ways of estimating the underlying distribution of your data. So there are many other types of distribution. There are super Gaussians, there are sub-Gaussians, there are mixtures of Gaussians, right? Or mixtures of any other distribution. There are non-parametric ways of estimating the underlying distribution. You can use any of those to estimate that distribution and then use that to define a metric to compute that. You see this? All these extensions are just trivial after this. Yep? Is that clear? Because it's going to be fundamental for everything else that we're going to do in the next 6 lectures. So, yeah. Okay, good. All right, so this is fantastic because now I have a method that I scan this window, and when my window is over a face, right, then that distance is going to be small, and I'm going to say, oh, there's a face here. So I already have an algorithm that gives me face detection. Now I still have a problem. I don't know the scale of that face. So the first thing that you could do is, or that we're going to do, is to try windows at different sizes, right? Different scales. And it's just computationally expensive, but right now we have no other way to do it, right? We'll see how to solve it later. But right now, that's the method, and that was the method for many, many, many years. Okay? All right. So great. We have face detection, and our life, it's easy, right? We can already detect faces, and if we can detect faces, you can see how you can extend these to other objects, right? Like faces of cats, or faces of dogs, or I don't know, maybe side views of cars, side views of motorcycles, right? Things like that. Okay? But there are a lot of problems. The first problem is, as I said here, that these faces need to be aligned with one another, right? Remember that we spent quite a bit of time with Procrustes alignment, right? And the reason for that is because the pixels in each image have to represent the same thing. If this pixel represents an eye for this image 1, but that same pixel for image 2 represents the nose, and for image 3 represents the mouth, then we're not going to find correlations, right? The correlations only occur when the pixels represent the exact same thing over and over and over again. So we need to align this. The problem is, it's a fundamental problem here. The problem is that faces are not easily aligned for 2 reasons. Number 1, all our faces are different, right? We don't have the same width, we don't have the same height. The distance between the eyes and the mouth is different for all of us. It's hard to align them, but we can do it, right? We can detect the landmark points, right? And the shape, therefore, and then do Procrustes analysis. And that's how it's done. Fine. We do Procrustes analysis. But that still brings us another problem, which is how precise can we detect these landmark points? Now remember that there was a question early on, I think a couple lectures back, on how precise can you detect these landmark points. So let's say that a landmark point is the outer corner of the right eye, right here. Well, this homework for you to do today. Go home, take a picture of yourself, upload it into an image software, and keep zooming in into the image until you see the pixels, and you can see the pixel that corresponds to the corner, the outer corner of the right eye. And I have news for you. It doesn't exist. But try it. I want you to try it because I want you to actually see how hard that problem is. That pixel does not exist. There's no one pixel you could say, oh, that's where the corner is, of course. No. If you ask, and we have done this, right? In my lab, we have done a lot of research on this many years ago, and we tested how accurate people can be when they identify that pixel, right? And many other landmarks like this. And it turns out that people are between 4 to 6 pixels off from one another, right? So if you ask 10 people, some people will say it's this pixel right here, another one will say this pixel right here, another one a little up, a little down, right? Each person will indicate a different pixel. Because the actual pixel does not exist, you just have to estimate, well, maybe it's this one, or maybe it's that other one, right? And every estimation is just an estimation. So how are we going to solve this? Because we need to address this for detection and, equally important, for recognition, meaning the recognition of identity. So let's see how we can do that. This is called imprecise detections. So imprecise localized faces. All right. So we want to do Procrustes analysis, meaning least squares alignment, right? So again, we have a set of faces, right? we have images of faces, and some of them are wider and shorter, and some of them are taller, etc., right? So we have many of those. So this is dot, dot, dot. And then, so this is my training set here, X, right? And I want to do least squares alignment. And we can do that, we know, using Procrustes analysis. So the first thing that we want to do is to compute the Procrustes mean. And that would be an image of a face, which is the mean face, right? And that means that I need to detect this number of landmarks that we were mentioning. So maybe the corners of the brows, the corners of the eyes, the tip of the nose, corners of the mouth, the chin, I know some other points here, right? And we have to detect those points using our already defined and known methods for low-level and mid-level vision. And then once we have this, compute the Procrustes analysis, which is going to, the Procrustes mean, which is going to give us this face, right? Yeah, question?
Going back to the face detection, when we did the training images, it was in the space of RP. But then when you have the new image and the face is smaller because you're passing a window over?
Oh, no, but they're all of p pixels, right? They're all of p pixels.
The window is?
Right. The window is a p pixel window. And if it's not, that has an easy solution, right? You just reshape it to p pixels.
Oh, okay.
Yeah, that's what people used to do.
Okay.
Right. All right. So you start with this. These are the original images, right? Now you compute the Procrustes mean, and then you use that Procrustes mean to create a new training set, right? So I take this MathCal X, and I create another MathCal, say, I don't know, X bar, right? Where now I have my Xi's bar, 1 through n, my training set. But now these have been aligned to the Procrustes mean shape, okay? And by this you use just any warping, right? A linear, nonlinear warping to warp the face onto that, mean shape. And that gives you the aligned faces. Now, this would be it if we could detect these landmark points with infinite precision. But unfortunately, as we said, we can't. So we somehow need to include in this some knowledge that we are making errors, that we are misdetecting some landmark points, right? And therefore, not all the images are perfectly aligned. So one way to solve this problem is to identify the distribution of the images of all these errors, right? So remember that I said we know, and I forget the exact number, but it's in the papers I posted in Canvas. I think it's about 4 pixels off, right? So plus minus 4 pixels to the right, to the left, up or down, right? That we know that the real solution is within that range of possibilities in this tiny window, right? So if I were to generate all the images with all these possible all these possible locations of the landmark, right? Then this would define a distribution or be an underlying distribution that defines all these possible vectors, right? Vectorized images. And I want to find that distribution, right? Now, if I have, say, m such points, right? there's 2m possibilities that it can generate, right? So depending on the number of landmarks, that number can be really high. So obviously you cannot compute all of them, but you can sample from that distribution, right? So you sample from that distribution, you generate some of these warps, right? And then instead of defining each image as a single image that's being aligned, you define it as a distribution instead, right? And again, the typical thing is to assume that these imprecise detected images or detections are, distributed according to a normal, or are normally distributed. How about that? Sure. Okay. So what we want to represent now in our X bar is a set of distributions. So let me call it maybe n sub I here with the corresponding mu I and sigma xi, I 1 through n, that represents the distribution of each of the images, right? And that little distribution defines all the possible detections of the landmark points, right? All the 2 to the q possible cases. Now, the only way to estimate that distribution, as I said, is you actually generate not all 2 to the q, because that's insane, but you generate as many as you can, right? As many as, depending on the resources that you have, you generate more or less. And once you have generated those, you compute the mean, you compute the covariance matrix, and that gives you an estimate of the underlying distribution, right? As we have done thus far. That's it. So that's the approach. Now, what's going to end up happening here then is that you're going to have now a subspace, right, as we had before, S, that defines all the faces. You're going to have all these different normal distributions here, right, that defines the samples. So instead of having samples now, you're going to have a lot of tiny distributions, right, like this, right? And all of these are going to be included, embedded into a big normal distribution, which is the big normal distribution that we had before, right? The same thing. You see that? Okay. So if we give name to these things, so say here, this corresponds to, say, the image xi, which has now produced my sigma xi tilde, right? And so on, right? So this could be sigma x1 tilde, sigma x2 tilde, and so on, right? All the x tildes. And now the metric that I had before, that metric on your right-hand side, at the very end that I had, I can modify this for any test image, say for DL, for localized or mislocalized. My distance now is going to be the minimum of my x. Did we say the test image? Yeah, test window, right? This is my test window is x. So I'm going to do the projection of x, which is x hat minus mu I hat times sigma xi hat inverse times x hat minus mu I hat. I'm missing transpose here, right? And what I'm doing here is note that I'm doing the same thing that I did here. It's the exact same equation. But now what I'm doing is I'm finding the distribution that is closest instead of the sample that is closest because each sample is given by a distribution. You see that? Is that clear? Yeah? Okay. Okay. Any questions? So this you can use to do detection and everything like this. There are more in the papers that I posted in Canvas. Obviously, there are more details about this and even more things that you can do, right? But this goes on and on and on. The thing in computer vision is, we give you the basic tools, and hopefully you see how these extensions that I'm building here are obvious one after another, and then you can just keep adding obvious extensions. And what I want you to do is to understand how obvious this is, because when you read the new paper 5 years from now, something that has not been done yet and I cannot define to you today, you can read it and say, well, this just follows from this, right? Just another extension, right? Okay? All right. So now with faces detected in an image, the next thing that I want to do is I want to recognize whose person that is. What's the identity of that person in that image, okay? And recognition of identities, what we usually call face recognition. So in face recognition, meaning identity, what we are going to have, we're not going to have our training set X. Our training set X for detection, which has a bunch of faces, right? Now, I have to say, because we're probably not going to have time to cover ethics, right? All these methods that we're defining now, this is the drawback. Okay, let me say first let me say the drawback first. The big drawback of these methods is that they are defined by the training set, the training data you prepare. That's why you have to align this data, right? You have to align that data, because if you don't align it, the algorithm will not work. It will not find the correlations. Well, if your data doesn't have both genders, let's say it only has males, now it will only detect males, right? It will have terrible high difficulty in identifying female faces because you're going to look mostly different. If you only include one ethnicity or one race, it's only going to detect mostly that face, that race or that ethnicity. If you only include one skin tone, skin color, that's what's going to detect, right? Until very recently, as still today, right, most commercial face detectors do not work with dark faces, which is silly. Why? Because the databases that we had until very recently did not include dark faces. It's absurd, but that's true. That's a terrible data set, right? It's a data set that is not going to solve the problem. That's a big drawback of these methods that we're introducing now. That never happened with model-based vision. Because we're model-based, because it's geometric, it's a shape-based methods, right? The shape is a shape. As long as you can detect the shape, everything else is irrelevant. The disadvantage is that you have to create that model. Here, the model is intrinsically given by your training data. So you see what we've done? We, if you remember, and there was a point about this also in this class, that the problem with model-based vision is that you have to create that model, and create that model is very hard because low-level and mid-level vision is not perfect. And that's not going to lead us to a well-described usually 3D model, geometrical model of our object. And then that's going to make it very difficult to detect or recognize the object or the identity of a person, right, in the image. Yeah, true. This method that I introduced today solves that problem. But it's not that it totally solved the problem. It just puts that problem into the data itself. If the data describes the model, intrinsically describes the model, then we're golden. But if it doesn't, then we're going to fail, right? So we've become now data scientists, right? And that's why data science right now is a big thing, because everything is in the data, right? Data science, big data, what all this means is that you create really huge, rich data sets that truly intrinsically describe the model. You don't know how to extract the model, but you know that the model is in the data. But that means that the model must be in the data, right? And that's easier said than done. I just want you to remember that. OK. So in face recognition, we're not going to have X, our mathcal X, right, that we had here for detection. But instead, we're going to have a set of them, right, many of them. So let's say Xj with J 1 through, let's say, C, right? J1 through C. And C the number of classes, meaning the number of identities that I want to recognize. Right, so I can define each xj as xij's, right? I from 1 through nj, let's say, right? Make sense? Now, can anyone tell me how I can now do recognition of identity based on the exact same approach that I had before? No one? Come on, take a shot at it.
Find the distribution for one identity and then find which distribution is closest.
There you go, right? I mean, that's what we've done with faces, right? With faces, we found the distribution of faces, and then find whether I'm close to that distribution. Well, now I find the distribution of each person, and then I see which of this distribution is closest to a new image of a face, and that's the identity, right? So now it's already trivial, so I can compute the argument of the minimum, not ij, rather, of x hat, or let me call it t for the test image, I think it's better, t hat minus mu j hat transpose sigma xj inverse hat inverse t hat minus mu j hat, right? And that argument gives me the j that is minimum, where mu j hat and sigma x j hat define the normal distribution of each identity, right? Of course, remember that we still have the localization problem that we defined here. So if we want to be even better, we need to define each sample not as a sample, but as a distribution, right? And then in that case, what we're going to have is the argument of the minimum j of the minimum I of t hat minus mu I hat, actually mu ij hat, transpose sigma xij hat inverse t hat minus mu ij hat, right? Yep. Where now j defines the class or the identity of the person, and I the ith sample in that distribution, right? I defines it's this xij, right? And each xij defines now a small distribution, right? A normal distribution that defines all the possible detections, including the errors. Yes?
So, when you said, just to check, when you said xj, the training set, so unlike in the imprecise localized faces where all of them are different faces, in this case, they all faces belong to the same identity.
To the same identity, correct, but many different faces of that person, right? Because you want that distribution of that person to include the variety of faces that you see under different illuminations, if you're considering pose, under different pose. If you're considering, I don't know, time, right? Or morning versus evening and so on. You know, all these environmental changes are going to change how you look during the day. That's what you want to model in that distribution, right? So that's it. With a simple equation like this, you can do recognition of identity. Right? Now, another problem with this is that these methods are not invariant to the expression, right? When I change my expression, when I'm happy, I'm angry, or I scream like crazy, right? The shading in my face changes, right? And there are two ways to solve this. One way is to have an xj, right, a math cal j, this set here, training set, that includes all the possible expressions. But what's the likelihood that you're going to have all the possible expressions for one person, let alone all of them, right? It's impossible. It's never going to happen. You're lucky if you have 10, 20, 30 images per person, let alone billions of different expressions that you can create, maybe trillions and quadrillions. So how are we going to solve this? We're going to solve this by defining a metric, as we have been doing. And what we want is to define a metric that is invariant to facial expressions, right? So I'm going to call this expression invariant recognition, okay? Okay, so expression invariance. I'm going to make my metric invariant to the expression of the face. Now remember from 5460 that we covered optical flow? What is optical flow? Optical flow gives me the point correspondences between two similar images, right? So if I have two different images, one for training and one in training, and one in testing, and they are of the same individual, and I compute the optical flow between them, it will tell me how the different landmark points have moved, right, from one image to another, right? So we can compute the optical flow between the test image and the Procrustes mean, which is the one that every image has been adapted to, right? And then what we assigned, so then we warp that test image, right, to emulate the Procrustes mean, but we assign a weight to each of the pixels of that image that is inverse proportional to the optical flow, right? What do you think I want to do that? Why do I want to assign a weight to each pixel that's inverse proportional to the optical flow? The optical flow gives me the point correspondences. I can now warp the image to the Procrustes mean. You see that, right? But when I do that alignment, I have an interesting problem in it. What happens? That I can align the shape, but not the shading, right? The shading is still the one of the deformation. If I had my eyes closed and the Procrustes mean has the eyes open, I cannot just all of a sudden make it appear sclera and irises, right? There's just going to be the eyes closed, stretched as if they were open, but the shading of the eyes is going to be completely wrong. So what I want is to assign a weight to each pixel that tells me how much deformed it was compared to the Procrustes mean. the more deformed that it was, the farther away that it was from the Procrustes mean, the most likely it is for that pixel to be useless to me, right? And I want to not count it. So I want to find, so first I do optical flow, and then define weights inverse proportional to the optical flow at each pixel, right? And if we do that, then the metric becomes the argument that minimizes the j, that minimizes the ith of t hat minus mu ij hat transpose w ij inverse t hat minus mu ij hat, right? And that w here is a diagonal matrix, right? Where the off-diagonals are all zeros, and the diagonal matrix corresponds to the weight that I have assigned to each of the pixels, right? Yes? Now, what I do, the way I do this is I compute, this should be w hat, obviously, right? So I compute my w, which is the diagonal matrix of w1 through wp, the p pixels, right? Oops. My p pixels, correct? And now I project this onto the space S, right? So I do, was it M, I think? M transpose Wm, and that gives me W hat. And then with my W hat, I can compute this metric, right? You see how this works? And that weight, this W here, right, this Wi, is inverse proportional to the optical flow. Now, how can you define a pixel that is inverse proportional to the optical flow? Well, there are, of course, an infinite number of ways to do that. One simple way, say that this is, let's say that I normalize the optical flow from 0 to 1, right? So if this is the optical flow here in the y-axis, this is my weight here, right? That goes also from 0 to 1. Then I want to have, when I have optical flow equal to 1, I want my weight to be 0, right? And when I have 0 optical flow, I want my weight to be 1, right? And I can just write a linear function like this. And therefore, I can, for example, say Wij is equal to the maximum of the optical flow of that ij pixel. I'm going to use a true norm, but of course you can use whatever norm you find appropriate. True, right? Oops, ij. Right, so this is the optical flow, so it is ij. This is the optical flow between my T image, my test image, and my mu, what do we call it? Mu ij, right? There we go. Okay, so you could also use a nonlinear function in here, right? So there's no reason why you should use a linear function. So for example, I could use an exponential function like this, exponentially decreasing function like this, because I want to say that as soon as my pixels start decreasing in optical flow, I want to give them less and less relevance, right? So I'm only going to give 1 when there is very small optical flow, right, or close to 1, and then all of a sudden I just want to go to 0 as fast as possible, right? Or you could do something in between, or even you could do something here, right? You could find nonlinear mappings that work best for you. Again, if you've taken my machine learning course, or if you take it or you watch the YouTube videos, you will learn about regression. So one way to do that, to extend this, is to actually find samples, right? Or to learn to regress that function. Let me call this function h, right? So you regress that function h that best maximizes the classification accuracy, okay? Or minimizes the classification error that we discussed. All right, so far so good? Okay, have a question?
What's the third index on Omega?
Oh, that should be Wij, right? This one, right?
Yeah.
Yeah, I don't know why I put K in there. Wij, yeah. Okay, so more problems. So all this is great. So far, so good, right? We can already do face detection and face recognition. This is progress. I can already solve two major issues that I'm going to encounter. One is, how am I going to detect landmark points as precisely as possible? And the other one is, what happens when I have different facial expressions, right? So we've solved all these problems. We have another classical problem, which is partial occlusions. Faces are typically partially occluded, right? Maybe I'm wearing sunglasses, and that occludes my eyes. Maybe I'm wearing a tall sweater or a scarf, and that covers part of my chin, maybe the mouth, right? I'm wearing a cap and covers the top of my forehead, and so on. So partial occlusions, maybe I'm standing behind someone else, and you can only see half of my face. Partial occlusions are a constant in face recognition, so let's see what we can do about that. All right, so one solution, if the occlusions are very minor, but the occlusions have to be very small, right? You could use robust PCA, right? So one solution. So one solution would be to use robust PCA that we have already introduced, right? Now that works okay if the number of pixels occluded in each image is relatively small. What happens if that's not the case? Well, let's see. There are many possible solutions, but let's see two of them. So the very first thing that occurred to us was to subdivide the face into local regions, right? So you divide the face into local regions. Say you can do 6 local regions like this, maybe 8, maybe 9, right? And then in each of these local regions, because each region represents the same thing in every image because they have been aligned to the Procrustes mean shape, then you can apply the exact same algorithms that we have described. The exact same algorithms. You don't have to change anything, right? Now, when an area like this is occluded, you just use the other areas, the local areas that are not occluded to do recognition, right? Now, if you do that, what you're going to get is a number of recognitions, right? So this is going to give you a an estimated j hat, let's call it 1. This is going to be j hat 2, j hat 3, and so on, right? So by j hat, I mean this result that you're going to get here, right? So this is going to give you some j hat, right? My estimate of the class that I'm recognizing, right? So I'm going to get a different j hat, and then there's several things that it could do. For example, I could do what's called a voting approach, that each local area votes for an identity, and at the end, the identity with more votes wins, right? That's actually a pretty good approach. Another approach is to actually add up all the distances, right? So instead of computing these different hats here, I sum over, right, here, over all the local areas, right? I sum over all the local areas, and then what I'm doing is for each local area, I get the distance, and whichever sums the least at the end is the one that wins, right? I can compute any statistic of these distances, etc. Right? You see how this works? So multiple ways of solving this. This is just a straightforward method to solving partial occlusions with the approach that we've seen now. Now, another approach, more interesting approach, is to consider reconstruction. So we'll call it, say, the reconstruction method. How about reconstruction approach? So here we're going to assume, as we have done 100 times already, is that my test image is nothing else than a linear combination of my simple images. Okay? Yeah? These Wij's are not these Wij's that I had here somewhere, right? If you want to change it, we can change it for, oh my gosh, I want to change this because my notes are with this, but maybe you can call them Aij's, right? I don't want you to be confused. They have nothing to do, right? This is just a linear combination, right? So remember that we did that in model-based vision, that we showed that you can describe the shape of every object, the 2D and the 3D shape of any object, as a linear combination of the 2D shapes of that object, right? Remember that? That's the same thing, but now with images, right? The pixels. You can define an image as a linear combination of other images. And now remember that the set xi1 through xini, right? This we have called the mathcal x, which is my Turing set for the ith class. Now, if I don't have occlusions, so with no occlusions, I can write that these AIs are equal to the argument of the minimum of t minus the sum from 1 through ni of wij xij squared, right? So here, what I'm looking for, right, this AI would be obviously AI is AI1 through AINI, right? Yep. And then here, oops, you see, I made that mistake. That should be A. Here, this is the least squares reconstruction error, right? Yes? So I see this is my image. This is what I have reconstructed. And what do I want? I want to find the AI that's going to minimize that error, right? The least squares error. You see that? Okay. Now, this is if I don't have occlusions. But what happens if I have occlusions? Well, actually, I can easily extend this to the occlusion case. With occlusions, I can write that AI is equal to the argument that minimizes, or actually not the argument, let's just say the W that minimizes, I don't like this. Let's just say the AI that minimizes T. This is the Hammond product M hat minus the sum from 1 to Ni of Mij, Hammond product of Aij times Xij squared, right? Where this is the Hammond product, which, remember, it's an element by element product. So if I have a vector A with A1, A2, A3, and a vector B with B1, B2, B3, I multiply A1 with B1, A2 with B2, A3 with B3, right? And I get another vector. And M is a vector, right, that has entries 1 if that pixel in my image is not occluded, and 0 if it's occluded. Okay, so Mij is equal to, or Mijk is equal to 1 if the kth pixel in Xij is not occluded and 0 otherwise, right? If it is occluded. And M hat, it's the same thing, but for my testing image T. Make sense? Okay. You see how this works? And that's it. You solve with linear least squares, and that's a solution, right? Now, I have to say, obviously, all these things that we have seen, and especially this reconstruction, does not need to be done with the square laws, right? With the least squares laws. You could use any other norm. Here you could use the P norm, right? So I could change this with P, and I could change this with P as well, right? So I could write here the P norm. I could use here the P norm, right? With P typically would be between 1 and infinite, right? But obviously P some natural number then. Right? 1, 2, 3, 4, 5, etc. But you could also consider, or you could consider a P be between 0 and 1, right? Or actually, let me make it strictly smaller. And remember, this is not a norm, but this is a quasi-norm. Okay. Now, it turns out, it's been shown that using quasi-norms is better. Why is it better? Well, it is better because the quasi-norm, remember, the true norm looks like this. It's a circle, right? This is the true norm. A quasi-norm looks like this, right? And what you are saying, as we were doing before, remember with the Wij's, what we're saying is that we want to decrease rapidly, exponentially so, right, to decrease the weight, right, when we see things that don't fit within our model, right? And that's a way to eliminate outliers, right? So when you're minimizing the least squares error, if you use the true norm, every pixel is going to count equally and squared. And therefore, the pixels that are most differently, right? So if I have one pixel that cannot be correctly reconstructed as a linear combination of other images, I'm going to give a lot of importance to that pixel. But it's just a pixel. So maybe I just can eliminate that pixel, right? That's what a quasi-norm allows you to do, right? It allows you to change the norm so that these pixels that have high distance from the reconstruction are not overweighted, right? And allows you to get better reconstructions, better solutions. The one norm also works very well. It's a little more difficult. I'll post another paper in Canvas about how to optimize the one norm. It's a little bit more difficult to optimize with the one norm. That's the only problem, right? I mean, the reason we love the two norm is not because we like circles or like anything like the number 2. It's because its optimization is trivial, right? In least squares, it's a pseudo-inverse. And if we're inhomogeneous, or all the equations equal 0, then it's a PCA, right? It's an eigenvalue decomposition. So that's why we like it. All right. Great. So I have at least 2 more methods I would like to go through, 3 more methods that I would like to go through as extensions of this. One is the Laplacian phases. The other one is linear discrete analysis. They're just extensions of everything that we've seen here. And the last one is tensor phases that uses the idea of tensors, or defines these things as tensors of higher order than 2. It allows you to solve a lot of these problems that we have defined here in a more compact manner. Okay? I'll do this next week. I'll see you then.